All right, so let's start. So today I want to continue with examples of Hamiltonian G-spaces and reduction. We start with a very beautiful construction due to Lerman, which is called symplectic cutting. So we start with the S1 version, and then we discuss a somewhat more complicated version for the torus. So let's say, as usual, S1 acting on M, omega, the 2 form on M, and mu, a smooth function on M. The Hamiltonian S1 space. Let me perhaps just briefly, for the students who join us for this week, just repeat the definition. So this means the following. M omega is symplectic, meaning omega is a closed 2 form, and omega righted in local coordinates, then omega ij will be known to generate matrices. So in this case, this would mean mu is S1 invariant. And this would mean that if you compute omega on the fundamental vector field induced by the action, so we can perhaps informally say it in the following way. So you have rotations by angle theta, and V is d over d theta. We obtain exactly the exterior differential of the differential of the function mu. So that's the definition of a Hamiltonian S1 space. So now let's play the following game. So let me recall that there is one particularly nice example of such a situation. So we can choose, well, let me call it N, the space R2, which I would like to identify with a complex plane. So it is acted by S1, where theta maps d to exponential I theta z. So it's just a rotation on the complex plane. So it has a 2 form omega naught, I over 2 dz wedge dz bar. And then one can choose the function mu to be the minus 1/2 of z squared. Right. So now let's consider the product of these two spaces. And let's say, let me call this form omega m. So with the 2 form given by omega m plus omega naught. And here I would like to equip it with an action of T2. Of course, one simple way would be to say that I take an S1 action on M and an S1 action on N. But I prefer to do it slightly differently. So let me say that this S1 is a diagonal is a diagonal action, so theta maps mz to theta acting on m exponential of I theta z. Right? And this one is just the action on m. So theta maps mz to theta m z. So you see there's just this slightly funny choice of those S1 actions. Of course, why not? I can always do it. So we take a diagonal action here and just the standard action on M here. So a claim, an easy claim, is that this is a Hamiltonian T2 space if I take the moment map mu. So let me call it mu1, mu2. And well, for the first component, I add the moment maps. Probably I should also call this guy mu m. Right? So here, this will be mu m of m minus 1/2 z squared. And the second one will be simply mu m of m. Right? Well, so in this setup, I can do reduction with respect to any of those S1 actions or with respect to both of them together. Let's do it with respect to the first one. So the first copy. So let me choose x in R such that the S1 action on the level set is free. And let me consider the space m cross n and do reduction with respect to the first S1 action at level x. So let me recall that by definition, so this means I consider the points mz in m cross, let me call it c, such that, so now I read the equation. So this should be equal to x, right? So mu m of m minus 1/2 z squared is equal to x. And I divide it by the first S1 action. Of course, I should still check that this is indeed smooth. I should check that the action here is free. So we're going to check it in a second. But for a moment, assuming that, this will be a symplectic space. Let me denote it m cut of x. So by our previous results, it's going to be symplectic. And recall, right, we started with something which had S1 cross S1 action. So we now did reduction under the first S1. The second S1 still acts happily. So this means that, in fact, this will be an S1 space. It's symplectic. And by our previous discussions, in fact, it will be a Hamiltonian S1 space with the moment map being the second component, right? So this mu2 will be, so mu m, mapping it to R, a moment map. So we basically built some kind of machinery which is given one Hamiltonian S1 space, produces for you many of them with a parameter. So let's check that it actually works. So we need to check that the S1 action, so that's, I recall, the first S1 on this level set. So MZ in M cross C with the condition mu M of M minus 1/2 Z squared equal to X is free. Now, well, it's more or less obvious for the following reason. So here there are two options. So the first option is, right, perhaps there are points with Z non-zero, right? So if Z is non-zero, then S1 action on C is free, right? So away from the origin, is free. And then the diagonal action is free, because if there is no stabilizer here, there is no stabilizer on the product. Now, well, what if Z is 0? But then this means mu M of M is equal to X. But we decided, so this was our assumption, that here the action on the level set was free. So then the action on the first factor is free. So here there are two subsets. On one subset, the action here is free. On the other one, the action there is free. So in total, it is free. Well, let me give an example of this construction. So recall that last time we were looking at CP2. And we were thinking of CP2 in the following way. We were saying that these are points of C3 such that sum of squares of absolute values is equal to 1. And we were dividing by the S1 action where you multiply all of them at the same time by exponential of I theta, right? This is a slightly, perhaps, non-traditional model of CP2, but this is CP2. So, so we were thinking of it as a T2 Hamiltonian space, where T2 acts in the following way. So it just acts in the standard fashion on the first two factors, and it doesn't touch the third one. So there is some standard symplectic form, and the corresponding moment map, mapping M to C star, which is now isomorphic to R2. It is mapping Z1, Z2, Z3. I don't quite remember. What did we choose for signs? Was it positive signs or negative signs? Positive. Very good. So it's mapping it to 1/2 Z1 squared, 1/2 Z2 squared. Right? So the And the image of this moment map, so the image of mu was a triangle, right? And here this, this form, perhaps it depends on some parameter x, right? It's just by, as a scalar factor. So this is a triangle which with coordinates of the corners x0, 0, and 0x, right? So last time we discussed that if we choose some y between x and 0, then for the action of the first circle, theta 1, so the first circle acts freely on this mu minus 1 of y, right? So that's easy to check. And now what? Let's do the cutting. You know, now we have many circles in the game. So here at the moment I'm not thinking of this second circle, right? So I'm doing my first circle. This means that when I do my CP2 cross C, so here I have S1 cross S1, and here I have S1. So in total, now I have 3 of them. So this one I don't touch. So this one I also don't touch. And then I do reduction with respect to the diagonal action of these 2. Right? So that's the scheme. Reduction on the diagonal action. Right. So let's imagine how it's going to work. For that, perhaps, let's for a second return to the. Let's return to this general scheme. The cut space. What is it? So these are points in M cross C such that M of M minus 1/2 Z squared is equal to X. And this is divided by S1. So we just said that the level set splits into a disjoint union of these 2 subsets. The subset where Z is non-zero and the subset where Z is 0. So the subset where, so let's start with the one where Z is not 0. So this is equal to MZ, M cross C, so mu M of M minus 1/2 Z squared equal to X. Z is non-zero, mod S1, disjoint union. So, and then the subset where Z is 0 is M in M. Here, mu M of M is equal to X, mod S1. Right? Now, this guy, we actually know what it is, right? It has a name. So we take the level set and we divide it by the free S1 action, right? What is its name? It's just the reduced space, right? So this is the reduced space MX. Now, what is this guy? Right, now we're saying that we can divide by the S1 action, right? And S1 acts freely on Z's. So this eliminates the phase of the complex number Z. But the absolute value of the complex number Z is completely decided by this equation. So claim this is isomorphic to the part of M with mu M of M strictly bigger than X. Right? So look at this equation. So we have mu M of M is equal to X plus this number. Of course, kind of if mu of M is strictly bigger than X, there are always Z's in C which satisfy this equation. Now we can divide by the S1 action by killing the phase of Z. So we completely get rid of Z. So we get this space. Let me call it M plus of X. So you see, it's actually kind of interesting what's going on. That's why it is called cutting. So we have our space M, and from M we have this function, the moment map, which maps it to R. Now we're choosing here point X, and that's a level set of X. On the level set of X, we say that there is a free S1 action. Now, what is the cut space? So first of all, this part where mu of M is bigger than X, we just preserve as it is. So here it is. So here it's open, right? Now what about this guy? So this guy we just divide by the S1 action, right? So here there is, so this is Mx, which is a quotient of the level set by the S1 action. Now the claim is that the cut space is a union of these two pieces of Mx and M plus of X. What is not obvious from this picture, actually this union is a smooth manifold, right? So this doesn't, at least to me, it still doesn't sound entirely obvious, but the construction tells us, right? We take a level set for a regular value. So this is a submanifold. It has a free S1 action. So the quotient is a smooth manifold. So this disjoint union, which a priori looks a kind of dangerous construction, probably these pieces wouldn't fit together. In fact, they perfectly fit together, and this gluing is very smooth, right? So even though it sounds a bit strange, right? Here you don't do anything, and here all of a sudden you decide to divide by the S1 action. So this is a smooth manifold. Of course, in particular, we said that the moment map here on this part, it will be just a restriction of mu m. This means that the image of the moment map will be everything like the image of the moment map of the original manifold intersection with the ray starting from X to and going to positive infinity. Maybe one more remark. So here we decided to take the upper half, right? We arranged everything such that the reduction produces for you mx glued to m plus of x. Remember that at some point we were discussing that if we change the sign here, the sign of the moment map would change, right? And of course, if we decide to change the sign here, then the sign in this equation would also change. Now, what would happen if you change the sign? Of course, all the equations would read in such a way that instead of the upper half, you will be getting this lower half, which would be glued to mx, right? So this would be M minus of x glued to mx. So so one can arrange signs to get this. Maybe the last remark, and this is actually the first exercise in today's problem set. So you may wonder what's the symplectic structure on this M plus of x, right? So it's reduced space, so there should be a two form there. I think later on we will be discussing in more detail what happens at this special locus. But what is your guess for the symplectic form there on the upper half? Right, so that's the first exercise. Just prove it. So I think it should be easy. So now let's get back to our example here. So we would like to do CP2 cut at a point y. We're not going to analyze it in details, but so let's discuss what is acting on this CP2 cut of y. Well, there is an S1 action which comes from the cutting procedure, right? We know that the cut spaces, they have an S1 action. And then, you know, there is this second S1 action that we were not touching at all, right? So there will be S1 coming from cutting, and there is another S1 coming, so that's the second circle action. So in fact, there will be again a T2 acting on this CP2 cut. Right? Kind of question, what do you think going to be the image of the moment map of this space, right? So it's a T2 space. It has a moment map. So what's the image of this moment map? Right? So this was the image of the of CP2 before cutting. Now we cut.
Something like sorry? Trapezoid or something?
Sorry?
Trapezoid or something.
Depends, right? If we now decide to cut, kind of, if we start with the positive thing, then it's going to be not a trapezoid. It's going to be a triangle, right? So you know, we choose everything along the first axis. We choose everything which is bigger than y. Right? So that's going to be the image of CP2 cut of y. Right? So here it was clear in the procedure. So we're doing cutting along the axis. We choose everything which has the value of the moment map in our cutting, which is greater than the value at which we cut. Now, that's a good point. What if we decide to do this negative cutting with a different sign of the moment map? So then indeed, right, if we take everything below y, so that's the image of the negative cut space. So CP2, let me call it minus cut of y. Now, so the image of a CP2 to start with was a triangle. So here we're getting again a similar triangle. So it's kind of believable that the corresponding cut space can be CP2 again. We're not going to analyze it in details now. But what is it for this trapezoid. Of course, some of you know very well the answer, but for those who don't know, or everybody knows the answer. So what's going to be this cut space where the image is a trapezoid? So,
Is it a blow up at some point?
yeah, it will be a blow up at the pre-image of the tip. Let me just say 2 words about it. So, right. So let me call this point A. Already in CP2, mu minus 1 of A, right? So this is exactly one point of CP2. So which one? So that's the point. What is it? How did I define it? I think it's like that. Exponential I theta 0, 0 for theta in 0 to pi. So right, divided by S1. So this is just one point, because if you want this coordinate to be, say, 1, we need Z1 to have absolute value equal to 1. And then since the sum of squares of 3 of them is equal to 0, the other 2 have to be equal to 0. This means we're getting just 1 point. So then the pre-image of this triangle is some kind of, let me call this point, I don't know, small p, is a neighborhood of P. So you're taking away some neighborhood of P, right, because you want to do the cut. And then you want to add the reduced space here. Remember what you do. So you're taking away, so we're taking away this negative part or positive part, and then we're gluing in place the reduced space. Now, what is the reduced space which corresponds to y? That we computed last time, right? So, and here, so the reduced space at y is again isomorphic to CP1. So we're taking away an open neighborhood, a kind of, we can imagine it as an open ball around the point, and we're gluing back as CP1. And that's exactly what is called a blow up. Maybe like slightly more, maybe not very precisely, but slightly in a little bit more detail. Suppose we have, so this is our M, here is our point. So let's say we're taking away a small neighborhood, but to simplify things, let's say to start with, I just take away a point here, right? And in place of this point, I would like to glue a CP1, and how I glue it. So I take this neighborhood, and in this neighborhood there are lines, and I'm glue. So each of these lines which goes through the point is like a copy of C without the origin, and in this point I'm gluing exactly this line in CP1, right? And it turns out to be a nice, smooth procedure. So again, here probably it would, I'm not sure whether probably in one of the algebraic topology courses you're probably doing it or not doing it so much, I don't know. So, but in any event, so here of course one would need to check that this is all smooth. Here it is all guaranteed by our procedures. What we are doing here is automatically producing for us smooth manifolds. Right. Okay. So now I would like to upgrade this cutting procedure to a multidimensional setting. So we now have a TK acting on M. We have omega 2 of M. And we have a map mu from M to TK star, which is isomorphic to RK. And we assume that this is a Hamiltonian TK space. So, well, let's again take some standard TK space. In this case, well, CK. So the action will be so theta 1, theta k, mapping Zi exponential I, theta I Zi. So we take the standard 2 form. And we choose our moment map just to be in components the same -1/2 z squared that we had before. Obviously, we can try to simply play the same game. So we want to define m cut of x for x, the point in TK star, to be the reduced space of m cross n at the level x. So maybe again here I should call this guy M, this guy M, and this guy, what should I call it? Mu CK. So this is as before. So points in M cross CK. So mu M of M plus mu CK of Z equal to X, and divided by the diagonal TK action. Of course, so now we decided to take a reduction with respect to the diagonal action, but the action on M still acts. So we get omega in omega 2 of M cut. So that's a symplectic form. And probably it's not a surprise that what will be the new moment map is simply equal to mu of M, as we had before. Right, so it's a kind of, after all, a strange story. We start with one group action, and then for free, we are producing two commuting group actions, which are almost the same, but still not quite the same. So one of them is just the action on the first factor, and the other one is the diagonal action in the product. Then we do a reduction under the diagonal action, but the first action is still there. That's, of course, because the tori are abelian, right? So they action commute with themselves, and that's why it all works. Now, of course, I presented you an optimistic scenario. So there is there is one outstanding question which remains. Which one? So this all works if what?
Action on the fibers.
Right, absolutely. So now we have to say, so this all works is if this action is free, or maybe if we want to relax it, at least we should say something about this action. So suppose we want it to be free. So it works if the following condition is satisfied. We still want this TK action on the level set. To be free. Perhaps let me write down this condition in details, in components, right? So these are k-dimensional vectors. So this means the following. So m of mi minus 1/2 zi squared is equal to xi. For all I.
It would be mu m of m plus mu ck.
Plus, yeah. Thank you. Right. So that's the set of conditions. So remember, before we had two cases, right? So one case was when z was equal to 0, and the other case when z was different from 0. Now, well, there will be many cases in general. So let's put it in the following way. So let me denote by I1, IS. So let me call it I inside 1K. Some subset of the set 1K. So we have such a multi-index. And so let's consider, so this level set will be disjoint union of the following subsets. Let me call it temporarily, let me call it, let me call it S. So S will be a disjoint union of I's, of SI's, and SI is an S intersection with a subset Z in CK, where Zi is equal to 0 for I in I, and Zi is not equal to 0 for I outside I. Of course, some of them may simply be empty, but so in any event, that's a that's a disjoint union. And now we want to discuss the freeness of the action on each of them. So it's we can also say that our TK it's a direct product of Ti and Ti bar, where this is a product of the circles with their indices in I, and this is the other circles, right? So this is just so this is S1 I1, S1 IS. Right. So it's already clear that Ti bar acting on Si, so this action is free without any conditions, right? Because this is so the corresponding Zi's, they are non-vanishing, and so the action on the corresponding action on the product of C's is free. Now we need Ti we need to impose some condition for the action of Ti on Si to be free. And say we can impose a sufficient condition. So it's a stronger condition than needed a sufficient condition. So let's do the following. So let's consider M in M such that mu M of Mi is equal to Xi for I in I. And let's assume that the action of Ti on this partial level set is free. So then for sure it works, right? So because so we have Si, so that's part of the level set where Zi's here are 0 and the other Zi's are not 0. Then we said that automatically Ti bar action is free, just because the action on complex numbers is free. But now for the i's in I, Zi square is equal to 0. So actually this equation is satisfied. That's exactly the equation that I decided to put here, right? And we assume that the Ti action there is free. So it's similar to the condition that we had before for the S1 actions. So there was just one condition. So we had only two. So maybe just let me. Sorry for being over time. Let me just finish this hour with the following. So if k, with the following comment, if k is equal to 1, then our Tk is S1, right? And then there are two possibilities for I. So I can be either empty or I can be equal to 1, to 1 index. So of course, if I is empty, then Ti is trivial, right? So no condition. So Ti is just a trivial group. So no condition arises. And if I is equal to 1, then T1 is just our circle. And the condition that we had before, the free action of mu minus 1 of x, that's exactly the condition that I have here. Free. Right. So this is a sufficient condition. Unfortunately, it looks a little bit cumbersome, right? So you have to have those partial torus actions on partial level sets to be free. But if this is the case, then certainly the Tk action on this space, which is stratified in the way as we described, is also free. And then the quotient is smooth. So we're going to exploit it during the next hour. How should we do? Should we have a 15 minutes break? Yeah, it's a good idea. So let's have a 15 minutes break. And sorry again for being over time. continue. So in this hour, I would like to give you an example of this construction. And actually, as it turns out, I guess most of you already know this example, maybe even in more details than I do, because you had this seminar about like stacky Delzans construction. And now we're going to do non-stacky, just a very ordinary Delzans construction. So, so we would like to do symplectic cutting in the k-dimensional setup. And to prepare it, we need some manifold on which we're going to do symplectic cutting. So, so let's consider the following example of a TK, of a Hamiltonian TK space, which will be the cotangent bundle of the torus TK. So let me introduce explicit coordinates here, right? So this is isomorphic to TK cross the dual of its Lie algebra. And so this is our torus, and this is just a k-dimensional space, Rk. So we can think of the following. Let me change it to n. So it has the following explicit coordinate system. It has angles θ1, θn, and the coordinates in the fiber I will denote p1, pn. The canonical 2 form is equal to, according to our general formulas, it's given to the sum of d theta I which dpi. So this space carries a Tn action just by translations. So phi maps theta p to theta plus phi p. So for the I circle, the fundamental vector field Vi is simply d over d theta I. And the moment map mu I of theta p, one can choose it simply to be equal to pi. We can also add constants if you want, right? So this is just a direct consequence of this equation. Right. Perhaps an interesting or a useful remark, if we take the image of mu, this will be all of Tn star, which is isomorphic to Rn. So that's on this space that we plan to do our cutting. Now, in order to do cutting, we should decide what will be our group action. Of course, it's not going to be very interesting if we do cutting under this Tn action. So therefore, we will make another torus, act on this T star of Tn, and so we'll define an action of some other torus, Tk, on T star of Tn. And we'll do it in the following way. We'll organize a homomorphism, a group homomorphism from Tk to Tn. Well, how does one produce such homomorphisms? Let's start perhaps with a circle. So there is a family of group homomorphisms from S1 to Tn that one can easily produce if one is given a vector M with integral coordinates. So then we can map theta to M1 theta, M2 theta, and so on, Mn theta. So this is clearly a group homomorphism from S1 to Tn. Perhaps sometimes we can write it also with the following notation, right? Exponential of theta is mapped to exponential of so this simply means that we do it everything mod 2 pi, right? So this is defined mod 2 pi, and the right hand side is also defined mod 2 pi. Well, now if you want to give a set of vectors in z to the n, perhaps it's also good to have a special notation for this z to the n. Let's call it lambda. So it's a lattice in our space Rn. And so we are taking this set of vectors with integral coefficients in Rn. So we take a set of vectors in this lattice. And of course, then we have this map. From Tk to Tn. Right. Perhaps here we need one small technical fact. And perhaps a notation. So let me denote this map by phi m. Right, so this phi m is depends on this set of integral vectors. Right? So phi m mapping Tk to Tn. Fact phi m is injective if and only if the following finite condition is satisfied. So we can take the set of linear combinations of those vectors with integral coefficients, and we can compare it to the the set of integral points in the corresponding vector subspace spanned by these vectors. So, and we can ask that all the points, all the integral points in this subspace be linear combinations of mi's with integer coefficients. Maybe I should, sorry. So the set of, so mi's are linearly independent. So probably this should be the first condition, and then this is the second condition. So the more kind of less detailed condition, or the easier condition, so mi's should be linearly independent, and a more tricky condition is this one. So maybe without giving a formal proof, let me discuss why is it true. So we want this map to be injective. So this is a map between tori. But then note that this condition, mi's are linearly independent, is the same as the injectivity of this map already at the level of vector spaces, right? So we can forget that we do everything mod 2 pi. We can just think of it as a map between Rk and Tn and Rn. So Rk to Rn map, which is just defined by the same formula. Right. So, and then of course, we do need that. Otherwise, the injectivity wouldn't work. Okay. Now, what about this condition? What does it mean that this map is not injective? So this means that so there is a point theta 1, theta k. Such that exponential of this theta 1, theta k is not 1 in tk. And this means that theta 1, theta k is not the point in 2 pi z to the n. But the image is 1. No, what I'm saying. Right? I think you should be correcting me. So it is not in 2 pi zk. Right. And this means that that this guy is in Right. So this guy is in 2 pi lambda. Right. Now maybe we divide everything by 2 pi. When preparing the lecture, I was long hesitant whether I should declare 2 pi equal to 1 or not, and then, in the end, what you see is a kind of trace of this hesitation. Right. So what we see that there is this linear combination of mi's, which is in lambda, right? So this is an element here. But we know that the coefficients are not all integer. So this theta 1 to pi, theta k over 2 pi, not in z to the k. So phi m being not injective, that exactly means that there are points here which are not in this span. So that's why injectivity of phi m means this kind of finite condition. Maybe one small remark. Assuming that k is equal to n. So then, so what these conditions mean together? So they mean that, so mi, which are now just n integral vectors, is a basis of this lattice lambda. So all elements of lambda are, so they are linearly independent, so they are basis of r to the k, but they are also basis of lambda because all elements of lambda can be obtained as linear combinations of mi's. Right. Okay, so now one more, or maybe a couple of more definitions. So our idea will be as follows. We have a space. We have a huge family of torus actions on that space. And we're going to do symplectic cutting under those torus actions. And we hope to obtain some interesting Hamiltonian Tn spaces. So for that, one more set of definitions before I can put all of that together, and that's now about polytopes. A rational polytope, delta, inside, let's say, Tn star, isomorphic to Rn. Is an intersection of a number of half spaces. So these are points in Tn star such that x with some pairing with some vectors mi is less or equal to some numbers li, such that mi's I lambda, li's are in R. I would impose the following conditions. Delta is compact, and its interior is non-empty. So let's imagine what I'm talking about. So these are combinatorial objects, right? Say, for instance, for n equal to 2, I can imagine, for instance, our beloved triangle that we already seen today, and this triangle is an intersection. So if these are coordinates, let's say x and y, right? So this is an intersection of three half spaces, and so we can have the lists of m's. So I think the first vector will be what? Minus 1, 0, and L1 equal to 0, M2 equal probably to 0 minus 1, L2 equal to 0, and M3 equal to 1, 1, and L3 equal to 1. Is it correct? This would be the triangle sitting at 1, 1, and if you want to move this coordinate, you should replace L3 with something else. So note that here the only, so these were basically just polytopes in Rn. The only requirement which was the rationality requirement is the requirement that I can choose those normal vectors to be in lambda. Right. And here they, as you can see, they can be chosen to be in lambda. Now, about Dilzahn, so now we introduce a more complicated notion of Dilzahn polytopes, and here I think there are some choices how beautifully or not beautifully you can make this definition. So let me try it out, and then maybe Benjamin is our specialist. He will correct me in case I do something wrong. So first of all, let me introduce the following notion. Let me choose an arbitrary point x in delta. And let me introduce, so let's say x is a point of delta. And let me introduce ix as a set of indices for which the inequalities are actually become equalities at the point x. So such that x mi is actually equal to li. So you see, for instance, here in this example, here in the middle, so this is a subset of 1K. So for instance, in this example, here in the middle, this set is empty. So here there is one inequality, which is satisfied. Here there is also one inequality. Here there is one inequality, which becomes equality. And in the corners, which are intersections of two lines, there are two inequalities which become equalities. Now, kind of all three of them, of course, can never be equalities, right? Because then it has no solution. So some of these sets may well be empty. But some of the options can never be realized. Some of the subsets are never realized. But for each point, you get this Ix. So here is a definition. The rational polytope delta in T star is called Delzant if for all x and delta, one has the following property. Let me state it. Maybe let me state it in the following way, as we did before. So the set of mi's with I in Ix. So this are linearly independent and ZMI for I in Ix is the intersection of lambda with the corresponding vector space. So the conditions are exactly the same as we had before. So we can say so the induced homomorphism of Ti, which is equal to the product of S1i's with I in I to Tn is injective. So see, it's a kind of, on the one hand, it's a tricky condition. But on the other hand, remember this story of multidimensional cutting. It is in some way gauged to this application to the multidimensional cutting. Right. In particular, perhaps note that so this polytope with those defining inequalities is actually Delzant. And what should one check about it? So we have some conditions to be checked for each x. Now, for x's sitting in the middle, there are no conditions to be checked because this set of indices is empty. Now, what about the conditions corresponding to the sides of the triangle? For instance, what about x being here? So if x is here, then the corresponding, so let me let me say, so x in 0 times 0, 1, then Ix, I think, is equal to what? To 1, right? So that's this index. So there is actually just one vector. Of course, now the linear independence condition is void. This vector is non-zero, so there is no linear independence. Now, what about this condition? So this condition actually tells us that if we take the corresponding line spanned by this vector, so that's just a horizontal line, right? So that's this line. So then all the integral points on this line, meaning just all integers, they will be multiples of this guy, which is correct. But it also tells us that here kind of we have this presentation of the polytope as intersection of half spaces. And of course, somehow we could decide here to write 2 instead of 1. The inequality would be still the same. However, we need to remember what this, we better choose those normals to be such that this condition is verified. Because if we define the induced homomorphism, it will depend on the value of the vector. So we want to choose the normals such that they will be of this form.
So we should choose the primitive vectors.
Yeah, we should choose primitive vectors when we can, right? But then sometimes it's going to work, sometimes it's not going to work. In a similar way, at the corners, right? We need to choose that the corresponding pairs of vectors will constitute a basis of our lattice. And here, this is the case. And you will see in the exercise 2 of the next problem set some examples where it works and some examples where it doesn't. And coming back to the stacky story, I guess where it doesn't work, then probably you have a more complicated theory. All right, so to finish this hour, let me now finally formulate the construction. So now we're building lots of examples. So suppose delta and Tn star a Dezant polytope. So in particular, it is represented as an intersection of hyperplanes, and I know that all these vectors are in lambda, and they verify the conditions that we stated. Well, now back to geometry, right? So here we dived into combinatorics. Back to geometry. So let's consider our M, the manifold, to be the cotangent bundle of this n-dimensional torus. And we're going to act on it by tk times tn. So tn already acts on it naturally. And now how tk acts on it? Well, we map it by phi m, defined by all this set of m's to tn. And tn acts on it. So this is actually, it's kind of this tk action is induced simply by the tn action. Now, maybe one thing. Note that typically for this phi m, cannot be injective. It's already because, see, for instance, in this example, so tk should be three-dimensional. We have three vectors, and tn is two-dimensional. So there is really no chance for it to be injective. So at first, it sounds a little bit strange, right? So this huge torus, so here there is a huge kernel in this action, right? So now there is a moment, there is, of course, the standard symplectic form that we write in our coordinates. And there is a moment map which is equal to mu tk, mu tn. So mu tn we know, and it is simply equal to p. Right? What about mu tk? Well, let me give you a formula and leave it as a simple exercise. But you see, since tk, so the tk action factors through the tn action, so this means you can construct the moment map for this tk action in terms of the moment map for the tn action. And actually, it's going to be like that. So it will be a k component vector simply given by dualities, evaluations of those p's on m's. So this is in RK, which is isomorphic to tk star. Well, now we can do symplectic cutting. And up to now, here we used up those data m of the so those vectors to define the homomorphism from tk to tn. Now, what about those li's? So let me choose L to be n1 lk in RK. So we'll define m cut at the level defined by the right-hand sides of the inequalities. So by definition, we know this is the reduced space of m times ck at level L. And this means so this is a set of mz's in m times ck such that mu tk of m plus mu ck of z is equal to L mod tk. And in more detail, those equations mean that P mi minus 1/2 zi square is equal to Li for all I from 1 to k. Right? Now, let me make two claims, and okay, let me very briefly discuss why they are correct, because we probably need to wrap up soon. So the first claim is a TK action on the level set is free. So this means that so this cut space is a smooth manifold. That's of course what we want. And the second thing is, well, of course we started with a TK action times Tn action. So this means that the Tn action gonna survive here. As usual, the corresponding moment map will be simply the moment map for M, right? As it was always happening, like every time before. So, and second, mu of M cut of L is exactly equal to delta, the polytope from which we started. So, and I say, probably you've already, I'm not sure, actually yesterday, have you already also seen this procedure in yesterday's lecture? Oh, I was promised. No, but you were discussing toric.
Yeah. It didn't stop what it did.
Okay, so but you don't recognize anything. Okay, so it was supposed to be some kind of catharsis moment, but okay. If not, then not. So, right, so maybe let's first briefly discuss this part of the story. So this is our Tn star. So remember that was the image. So that was the image of the moment map mu m. So the moment map mu m. So this one, right? It just the image is just the full n-dimensional space. Now you start doing cutting, and now we know how this cutting works. So we're taking those S1s, one after another, and we're trying to solve those. We're trying to solve those equations. So in those equations, we see that so these guys are always non-negative, which means that on the solutions, the duality, the product between P and Mi will be less or equal to Li, right? So that's just the consequence of those equations. So that's how it happens. So from the image, we'll be cutting those half spaces for all i's. Well, I'm not sure that what I'm drawing is actually good, but so there will be many of those inequalities, and in the end, our polytope will emerge as it happened before in the examples and in the procedure. So this is more or less easy. Now, this is not entirely easy, but let me still say one or two words about it. So why is it true? So why this action is free? Well, again, what we do, we say that the level set S, which is Mz in M C star Cn cross Ck with all those conditions, Pmi minus 1/2 Zi square is equal to Li, is a disjoint union over i's of S intersection with the condition Zi equal to 0 for I in I and Zi non-zero for I not in I. So and these were our SIs. So recall that we need to check that Ti acting on Si is free. Right. So it turns out that if Si is non-empty, then this means that there is a point x in the polytope such that I is equal to Ix. Right, and then by our Delzahn condition, this means that the induced map, so the map phi m restricted to Ti from Ti to Tn is injective. Right? So that was in some way the whole idea of the story. So those Ti's which actually exist in nature, so they embed into Tn injectively, even though the whole Tk has no chance to embed to Tn injectively. It's just much, much bigger. But all those Ti's, they do embed injectively. But recall that the Tn action on our manifold is simply by translations. So the Tn action is free. So everything which injects into it acts freely. Right? So this means that the corresponding Ti does act freely, and not only on the level set, on the whole manifold. Right? We remember our sufficient condition was to check that there is a free action on some partial level set. But here, it doesn't matter. It's just free everywhere. So this means that our sufficient condition is satisfied, and this means that this corresponding cut space is actually smooth. So see, this is a complicated, very complicated example, but very interesting example. So, and all of a sudden we produce like whatever, again, zillions of those Hamiltonian T-spaces. So this part of the course, maybe it was not sufficiently structured. So we introduced our definition, we proved the reduction theorem, and now we gave several big classes of examples. I think next time what we're going to do, we come back on our kind of more standard track, and we have two big theorems to prove still, at least two big theorems, the convexity theorem and the localization theorem. And so next time we're going to discuss the convexity theorem. Perhaps we state it and maybe we make essential steps towards the proof. Yeah, sorry again, like kind of, but this story carries you, right?